Today we've got Edward Komet, author of the Haskell Lens Library, among many, many other things. He's going to tell us how lenses are actually useful in business. Take it away.
So I'm going to throw the floor open pretty much the entire time. So at any point in time, if you have any questions, you want to interrupt, feel free to stop me whenever. This is actually going to be fairly unstructured in some ways. So I originally wrote lenses for me, not the lens library that we have for me. Sort of as a little bit of a background story here, what happened was I had written a library called Data Lens in Haskell based on the co-state, co-monad, co-algebra way of working with lenses, which Russell O'Connor had explored in some blog posts and a paper or two. And I found when I was working with them, I kept running into cases that I couldn't express in the lens vocabulary. So how many people here are not familiar with the notion of a lens? Let me start there. Okay. Huh? I will assume lack of familiarity with all of the details of the lens library. I would have a very small audience. I probably would have to exclude myself as well. So when I was getting ready to do this talk, the other day I put out a comment on Twitter asking for lens testimonials, and I got some things back, about all these wonderful things about how they're using them in different situations for working with functional state machines and working with representations of CUDA code and JSON. And there are people out there using these for XML. And that last comment actually is not a comment about the usability of the lens library, but it's in Japanese, so you can't tell. And, well, okay. People liking using it with the reader monad or with state. And then I started mining a little bit further and generating GADT code in C#. There's people now who have ported the lens library to PureScript. There's a working implementation there, which includes prisms and all the things. Julien Truffaut has an implementation of it in Scala called Monocle. There's a port in Scala Z itself. So there's two pretty usable implementations of lens in Scala. But there's been a number of, as many positive comments as I get, I also get complaints about, someone goes to reach for a lens library and they pick out lens and they go to pull. And, there's this sort of recurring meme that there's difficulties of different Haskell abstractions. That, monad transformers and foldable, traversable, and applicative, but lens. So there are things I am not proud of and aspects of it that I really am. So when I put together the library that we have, I should actually probably grab this rather than just scream very loudly. I was building a library for me, not for users. I was working on a random game development project because I was bored that day. And I wanted to build I think I mentioned this during a lightning talk the other day. I wanted reproducible physics, so I wanted a functional physics engine. So once I needed a functional physics engine, I needed linear algebra. Once I needed linear algebra, I needed a representation for the individual bases for my vector spaces. And I chose to use polymorphic lenses into the vector space. So that's where lens came from. It sort of subsumed the original goal, and I never actually got back to the game. And so I put up this horrifying little diagram, which unfortunately washes out on the screen, this UML diagram like thing that we have for our field accessors. That way I could try to make the object-oriented programmers feel at home in Haskell, because that way even our field accessors have UML diagrams describing how you use them, And there's a number of objections, well, not just objections, just sort of general concerns about the complexity that I get from folks. Maybe I'll have an epiphany and understand it someday. Lens is why I quit Haskell. If you want to look at the glyphs in the lens library, type man perlvar. Dan Haraj talking about not having had to scoop his eyeballs out with a melon baller. And the process of searching the Lens API. It's a Swiss Army knife that weighs 10 kilograms. Or, if you're looking for Lens job security, just Lens all the things, right? So it's all taken in the spirit intended. And so, there's actually a pretty straight port of the basics of Lens inside of PureScript, the Monocle version of it. But even if we look at the PureScript implementation, we wind up with little comments like this. So I feel their pain, right? And there's a whole cottage industry of Lens libraries that have come out of it not wanting something simpler. Okay, and so we had an applicative Lens proposal, which actually isn't really a Lens library. It just got caught in the dragnet that I threw over Hackage. There's FC labels, which actually predates Lens considerably. Lens family, which predates Lens by about a week. Data Lens, which I wrote and then gave away. Data Lens Lite, because somebody didn't find that one light enough. Reasonable Lens. No judgments placed there. Put Lens. Small check only Lens uses it. So it's a micro lens, and there's various other ones. And so each one of them tries to implement some small subset of what the Lens library does. And of course, nothing of value is lost in the process. Or is there? And so that's what I want to talk about today. I want to talk about some of the stuff that's in Lens that feels weird or big or unhaskily or bizarre. And just maybe get a little bit of a sense of what some of these weirder objects are. Because we go back to that UML diagram, there's we have folds and setters and getters and traversals and lenses and reviews and prisms and ISOs and equality. And now this, I don't know, 1, 2, 3, 4, 5, 6, 7, 8. This is, I think there's 45 different synonyms for, type something in Lens that sit there in a user-facing fashion, and it is admittedly somewhat daunting complexity. And if you look at the documentation in Lens, we're actually very careful in all of our combinators that we can to turn around and provide you with some common sense explanations of what these things do. Like, give examples. We have thousands of examples at this point in time. On the other hand, we have thousands of combinators. So maybe the ratio could use some improvement. All right, so with that, let's see here. So I should be able to flip back and forth between various. So it's picked up a few reverse dependencies, slightly more than it has forward dependencies. 472 reverse dependencies. I think 50 of them are those Amazon bindings. I'm not kidding. It's used now by Diagrams, which has recently adopted Linear for its internals. So if you've seen Brett Yorgie's Diagrams work, that is now Lensified. Snap, I think, was the first web framework to come on board. Now more of the web frameworks are using lenses internally. What else do we have here? I mean, it's pretty weird. So Diagrams, it was only about 10 of the reverse dependencies. So there's a lot of things using Lens, and I will freely admit I have done my, I probably owe the world penance in terms of the carbon that I have caused the computers that process Haskell to emit. So I apologize. I may have tried to optimize for developer time, but I have definitely not optimized for the number of CPU hours that people have used compiling Lens. Okay. So again, the Data Lens library was my first foray into the space, but the problem with it was that if you went to go use this notion of a lens, this is, we can absolutely make it bigger. There we go. So in a common sense level, a lens is a pair of a functional getter and a setter. Okay? That I know how to get some part out of a hole, and I know how, given a new version of that part, I can put it back in. Okay? That's what a lens does. We can build a category on lenses here, which says that if I can zoom in on one part of a hole, and I can zoom in on a part of that, I can compose these things and zoom in further. I have an identity lens. I mean, they feel really nice. And then we started playing around, and we built, these are the old data lens combinators, but we built lenses for getting into pairs and maps, or so if you wanted to look at a particular key in a map, we can actually zoom in and tell it whether it's there. You can actually write back nothing and delete the key from the map. Or you can put just something and you can change whether it's even present in the map at all. Sets, we can actually write back to the indicator function. We can read out if something, if it contains something. Okay, so I'm going to leave data lens behind. So the problem with data lens was that as I was working with it, what I was finding is if I needed something that was just a little bit outside of the vocabulary of data lens, I had to stop everything I was doing, throw out all of the code, and start all over. Okay? Because I wrote with lenses, and I was able to compose in and build a chain, but now I have to look at two things. Oh, crap. And there was no way to fix this in the old vocabulary, right? The one that felt pretty Haskell-y was largely unsalvageable. Okay? And so back, I think actually around 2007 or so, Twan van Laarhoven wrote an article on functional references where he gave the what we now call the van Laarhoven lens representation, this A arrow f of b, s arrow f of t thing. And what I will do is I will flit in and out of a Vim session here, which I probably should have sized beforehand. Let me know when I can stop making it bigger. You're good. All right, good, because all right, so the type of lens that I want to talk about is this thing. All right, so what is that? A stab? Doesn't really make a lot of sense. Why is there a functor involved? I was talking about getters and setters a moment ago. Where the hell did they go? You know, I get a lot of this, right? Why am I throwing a functor in the mix? It doesn't seem to make any sense. But let's just look at what this thing has to do. And then we can simplify the signature to this thing, where we're going to get rid of the redundant seeming parameters. Okay? But if we just look at this type gives us a little bit more information. I really should have grabbed my laser pointer. So here, if I wanted to call this, you give me a function of this sort, it doesn't know anything about your choice of f. It doesn't know anything about, so you're going to be given a functor f. And so you're given a functor instance for f, and I'm going to give you a function from a to f of b. And you have to somehow get me an f of t. So the only way that you can get there is if you take that function and apply it. But you have to apply it to an a, and you don't have one. You have an s. So you have to have some mapping that gets an a out of s. Right? So you feed that, now you've got a f of b's. Now you have s still floating around in your environment, so you can use s, and you can use b, and now you have to get to t. Okay? So this is where the getter and setter pair come from, because what we have to have is we have to have a function from s to a, and a function from s to b to t. Now I kept the arguments split, but if we work down here, then this is the common sense notion of a lens. It's a getter and a setter paired. Okay? And now the trick is then trying to figure out choices of f that let us, this is the game of lens, is trying to find functors that I can use to recover those individual functors, or those individual functions. Okay? And there's a number of choices here that we can make. And if this was a ICFP talk, I would probably spend the next 45 minutes talking about all those choices. Okay? But I'm really more focused on what you can do with a lens today than on how they're built and how they all fit together. The nice thing about lens is that things fall together for very fundamental reasons. If we look at the type of traverse, which is now in Prelude, this almost has that same signature. If we squint at it, here's the a arrow fb, and I've got something to f of something, right? So if we, unfortunately requires alpha renaming without capture in your head. If we rename this to s, and we rename this to t, we get more or less the signature we had, but with a stronger constraint. We now have applicative. So you could think of a traverse as saying that if you gave me a traversable t, then I will give you what we call a traversal STAB. Sorry. TA, TB, AB. Okay? And if I ask for that, it type checks. Okay? So this is just putting, when we start talking about traversals, a traversal is a lens that can hit multiple targets, in some sense. Russell O'Connor used to originally refer to them as multi-lenses, but for branding, they've been renamed traversals. So we have lenses, and it's not immediately obvious why this notion of this version of a lens makes any sense whatsoever. But what we could do is, if I wanted to write a lens for working with, I don't know, the second member of a pair, and what I can do is I can take the function you've given me, and let's try and avoid a name that would cause conflict. There, we will then do that. So that is the implementation of a lens. Notice I didn't use anything outside of the prelude. It's sort of the social hack that has enabled Lens to infect as much of the Haskell community as it has. So I apologize for that. But it really is that _2 is a lens. I'll write it with prime here. CAA. And I can get an A out of a CA pair. So it zooms in and looks at the second half of the pair. Now, if we remove this prime, we get an interesting result. As a matter of fact, we discovered this by just not writing the signature. And then I had to figure out laws for this retroactively, which actually turned out to be a nice, basically the functor laws, just in a very interesting choice of category. So we can sit there and write down _2, and if I turn on the Haskell extension soup, I need rank n types. I can type check that. Okay, so I have _2. I need something to do with it. I need to be able to do something with it. So let's make a combinator that can view the result of a lens. Okay, I realize I said I wasn't going to get lost in the weeds here, and I just got lost in the weeds. So here what I'm going to do is I'm going to go grab const from control applicative. We'll say view is going to take a, actually I'm not going to bother to write a signature. That was my lesson from the first time. I want to get view some lens at some value, and I want to say, hey, apply the lens to the const functor on S, and then get const to unwrap it. So if I view _2 out of 1, 2, it should get 2. Okay. Hello. World, and we can get world out, right? If I look at the type of _2, it has the sort of messy, weird lens signatures that GHC expands and makes completely unintelligible. And when you screw up, you get absolutely mind-bogglingly awful type errors, and I apologize. I just don't know how to do it any better. So with view here, what do we have to do? Well, you gave me an A to a const AB, S to a const A S, or const AT, and I will give you S to A, because that's what this does. And type checks, okay. So we now have the first thing that we can do with a lens, and then the other thing that we want to be able to do is maybe be able to write back to it. So we hold that over, and I'm going to use the identity functor as my choice. I'm just doing this to convince you that you can actually reason about these things. So here, if you give me A to B, I'll give you S to T, and how do we do over? Over F is run identity.L identity.F. Did I typo something? Oh, yeah, that helps. It's kind of useful pair programming with this many people. All right, so with that, over _2, I can say, hello, what do I want to do? I want to use, I don't know, length. And hello, world. This is the only lens I have. And now I can actually change the type of what I looked in there. Now we're in a strongly typed language. I just walked into a pair and changed out the type. It's kind of nice. And here I can say, oh wait, I should put it the other way. That way I don't need an _1 or, yeah, okay. So _2, _2. Okay, so now this one's getting a little bit weird. We've been able to compose our lenses by using function composition. So why does that work? Okay, so what I want is that and sort of the core hack of lens, other than the social aspect, is that dot becomes the object-oriented programmer's dot. Okay, so we are able to hack function composition to be object-oriented field accessor. Okay, and we can make this even more atrocious by defining an operator, caret dot, which starts us off with, I won't even bother to write a signature. I will just say S to this lens is view LS, and I probably have to put a fixity on it in fixer 8. I don't remember. We'll find out the hard way. So if I say hello world and read out _2, it works. Okay? And if I use read out _2 dot _2, it works. So I can chain field accessors, and we just have to start off the chain with this caret dot. So the caret points to the thing that you're working with, and then dots compose all the way through. Now this works with every one of the abstractions in Lens. So for those of you who aren't familiar with the library, this is one of the things that has sort of made a lot of Haskell code more terse. Other people may disagree about whether it has made it better or worse. I will leave that to you. I'm trying not to take a stance. Well, I'm taking a stance here. I think it's made it a lot better. But so be it. Okay. So now we can also do things like, oh, I don't know. What did I do here? Over _2 _2 traverse, why not? Yeah, I need an _1. You know what? We're going to write our first traversal, just to. I'm going to work with, give me a pair. So, you know, traverse always has to work over the second half of a pair because it's the only thing it can do. But we could write a combinator like this using applicative. I don't know, what did I typo? I didn't define traversal. I haven't brought in the lens library yet. I'm trying to put that off as long as I can, just to make this feel motivated. Sorry, I guessed wrong on the screen width. But regardless, this is the same thing as a lens for all intents and purposes, except for that applicative constraint. So now what I'm allowed to do is, before we had this assumption that the only way that I could build an F was by calling my function. Now I have more that I could do. I can use pure, and I can use app. So I can call that function multiple times, and I can stick the results together. And I can use pure to build one out of whole cloth. So we can make a really boring traversal. So is a perfectly legal traversal of anything you want. It's happy. And we have both, which is another legal traversal. So we can play games with hello world. I don't know, what else do we want to do here? We need to tuple these things up correctly. Da-da. And I've got that thing, so let's do oh gosh, over both sides of this. There, ha. Both sides of that, traverse, and compute suck. So, yeah, it's maybe not the most readable result, but it did the thing that we asked it to do. All right, so we can drift in, we can use both. That composed a whole bunch of traversals, but I can just as easily, if I had, yes, compose in a lens into the mix. Why? Because a lens is a traversal. If we look at the type signature that we gave, a lens is just a traversal that ignores this whole, downgrades this applicative dictionary to a functor. It says, I don't need the applicative stuff. Just give me the functor that's at the core. So I'm given an arbitrary applicative. I can use less. Okay? So with this, we're able to build all sorts of other horrible abstractions just by choosing interesting choices of F. And with this, I was able to get a whole bunch of interesting things that let us model getters and setters, read-only and write-only, notions of operations to access bits and pieces of your data. Okay? Traversals let you hit multiple targets. Setters let you actually work underneath functions. And when we go back and apply these things to like the linear algebra primitives, I should be able to like, I don't know, linear V3. Oh no! I'm gonna have to install something. I'll have to go in the background. Anyways, we can then use those in a number of interesting situations, which I will get to later. The combinators that we have for working with lenses are very much sort of inspired by the ones that you have in C++ and other places. Plus, equals, all of these operators, which are another source of the crap that I get for writing lens, is that you can write all of your imperative code, but now if you think about it, you can actually reason through it because you actually have state, and like plus equals is fishing something out of your state from a given lens, applying the modification, and then putting it back. Okay, it's not sticking you with Hoare triples and imperative state. It's actually a pure function. Okay, so now all these other lens libraries do all this stuff. So now traversals are starting to catch on. But one of the things that they really haven't caught on to are these things that we have in lens called prisms. Okay, and so the name prism is, lenses got the notion of focusing in. I realize you can have both concave and convex lenses so that the intuition really doesn't help. But that's what we chose. That's what the name lens kind of started historically meaning. So we needed a name for kind of things that we can split apart. Okay, and the notion of a prism is analogous to a sort of smart constructor. Like if I have a traversal for, say, the right-hand side of an either, then I could walk the right-hand side and change its value if it's present. But it doesn't let me construct. Right, so with a lens, I was able to get, oh no, I lost my session here. Shoot. All right. Oh, it's in a different window, great. I have to look at my schedule. That lens position window. I am not, no, not my iTunes. All right, so we've got linear. So with a lens, I was able to get, that's what I get for switching windows. All right, and set, right? I had a getter and a setter pair. I had the ability to like S arrow A and S arrow B to T. If we kind of tuple this up and squint at it, what is this really trying to talk about? There's another representation of lenses that folks have talked about a fair bit. Tuan, actually, the guy who came up with Van Laerhoven lenses, doesn't really like Van Laerhoven lenses. He likes these other ones where we say, what if S was actually isomorphic to some pair of C and A? C being this constant complement, I think, would be what the Bucks, the bidirectional transformation community would call this. And the data, the piece of data that I want. So this is saying that there exists, I'm making up a symbol for isomorphism, some kind of C such that my whole is isomorphic to the part that I'm interested in and all the other stuff. Okay? So this is one, and if you actually chase down this notion, you can actually make this work in any symmetric monodal category. And, yeah. Anyways, nobody here cares. But what I can do is I can talk about what happens if I start playing around with the right-hand side a little bit. So what if S is isomorphic to either the thing I want or anything else it could be? Okay? And this is where a prism comes in. A prism is a smart case. I can use it, it's a smart constructor. I can use it to build, and I can use it to match. And here I'm actually going to go load up the real lens library rather than start re-implementing them because those get hard. But we can start building things like with the underscore left prism, I can build underscore left, which isn't terribly exciting because we could of course have done this with that. But if I had left 4, and I wanted to match, to check to see if this was left, I can do so. Okay, so this caret question mark operator works on prisms, but it also works on any traversal. It'll give you the first match of the traversal, the first thing that it hits. Sort of a preview operator. As a matter of fact, we call it preview. And you flip it. So we can do that. If this didn't match, you'd get back nothing. If we used this to update, we could go through and do things like, now that's kind of simple soup, but and is actually very simple to implement. It's x and f is f of x. It's flipped application. So this is flipped application of this. So this is take a lens and something I want to do to it. In this case, I'm adding 1 to it, and then apply that to this thing, which gives me back a pure result. Okay, so symbolic, like it's, the goal here was to get something that felt fairly native to a C-ish style programmer. Maybe that's a laudable goal. Maybe that is anathema.
What does it do when it doesn't match?
Well, when it doesn't match, it silently says, okay. Let me go back to, where do I have it? Left, right, left, and left, right, plus equals, I don't know, 5, therefore, there we go. Oh wait, I should have chosen a different number. So here we've gone in and we've tried to match, and this has matched all the occurrences of left, right, which there are 0 of. So that's somewhat, I believe I have a combinator called failover, which takes these lovely type signatures, which takes a setter of, a traversal, and then lets me say, hey, add 1 to left 5. I should not be asking for the type of that. I should be doing it. And then if I go to apply it to something else, it gives me a horrible error. Wait, which one am I thinking of here? I have got the wrong combinator, and I don't remember the name. Great. Oh, it's using M. Because this implicitly chose I/O. Oh, come on. This is what happens with lens. So, so be warned, there be dragons. But there is a combinator that you could theoretically use to try and make that thing nice. Anyways, not my music, not my schedule. All right, somewhere back here. One of the things that we cared about prisms for originally was for we have in Haskell, we have an extensible exceptions hierarchy. Okay? And it's actually kind of a pain in the neck to use. If you go to use catch, sorry, Simon, with extensible exceptions, then you usually have to do something where you actually use the constructor, or you have to put a pattern, or you have to put a scope type variable signature on it, or you have to do something. Okay? So one of the things that we were able to do with Lens is make it so that you can catch pretty much any fold. So you can say, if I had a fold that knows how to read from some exception, a prism is one such thing, then I can handle that case and it'll match. So if I look at something like this, I have underscore assertion failed. Lens likes to take names that aren't used, and so at the time, leading underscores were a rather underpopulated portion of the namespace. Now, they were legal identifiers, they still are, but now we have all of this typed hole stuff, so they half the time get recognized as type holes. But as long as you write code that doesn't go wrong, all's good. So here I can do catching for a particular thing and then throw it off to the side, or handle. And what we're doing to make all of these things go is we have a little, let's get past all of this stuff, an as arith exception class that lets us say an arithmetic exception is possibly an arithmetic exception. Well, that's not terribly deep, but some exception is also possibly an arithmetic exception. So I can give you the prism that matches the arith exception case. Okay? But then we have things like this. I have underscore overflow here is a special case of the arith exception. So this prism matches on the sum exception and comes down to the arith exception case. But then it comes down further into, like if we look at arith exception, it has underflow and overflow and these different constructors. So I can then match on the particular constructor. So I can catch a particular constructor out of a extensible exception. Okay? And then since this works for any fold, I can also do things like filter based on properties of it. Okay, so now this one didn't have any particularly interesting properties, but I might want to maybe be able to match on something on the string in one of these things, or I don't know what we have lying around here. We don't really have too many. If we start playing with I/O exceptions, there's all sorts of structure you can dig into. So to me, this was one of the telling moments for Lens, was when it started being able to take an existing API and make it a lot nicer to use, right? We didn't design the extensible exception hierarchy with Lens in mind. We just started dealing with something that happened to involve an open sum. All right. So this was the first real world use case that we had for prisms. And there's a number of, Lens, out of order. There's a number of other libraries out there that implement enough of Lens to be able to do this. In the Scala ecosystem, if you don't have the privilege of being able to convince your employers to let you work in Haskell and you have to use Scala because it runs on the JVM, then Julian Truffaut's Monaco library is a passable alternative. It does about the best you could do within the confines of the Scala type system. And there's also, in PureScript, we have the other one that I mentioned. And there's libraries for dealing with all sorts of other things that happen to be made out of possible cases. For instance, for working with, here's a, let's play with HTML markup and come in and say, let's go get the elements named with a name that is length 3, or go into the element tag, get the element's name, etc. You can do a ton of different sorts of filtering where the attributes match on this, that, and the other thing. Drill in and then change out those values. You can start with a piece of XML, some horrible thing that's been fed into whatever REST API that you have to deal with in your day-to-day existence. Even if it's not XML, we can do JSON, because JSON is also made out of cases. It's either an object or a array, or it's a string, or it's a number. There's a very small set of cases to consider. And we can construct all of those things with prisms. Now we can go in and we can look at all the parts by traversing the individual components, or we can construct from the bottom up a piece of JSON without ever having to know how to put it into a really nice Haskell-y data type. And if you're the guy stuck between two web services that you don't know anything about, you can turn around and say, let me take this JSON document, munge it in the particular way that I need it to go, and then shove it off to the other. And this is, as much as I don't want to admit it, a large part of what people out there get stuck doing. Okay, and so this is the part where lenses took off and I wasn't planning on it. I was planning on using Lens after I got through with playing with it for linear algebra on field accessors, right? And every time somebody starts talking about the field accessor problem in Haskell, they start talking about, oh, I've got a record and I need to get at one of the fields. But here I've got a record that has a field that has a map in it, that has a data type that happens to be JSON, and I want to go in and manipulate different pieces of it. All of those things composing together is what really let Lens take off. And it's somewhat telling to me that out of all of the Lens implementations in Haskell, the Lens library is the only one with the Prism construction. So there's a lot of people who tell me, well, why don't you, advocate using micro lens or reasonable lens or one of these other ones? It's because half of the thoughts that I want to think inside of the abstraction are now cut off from me.
Question about that.
Absolutely.
So, are there plans to merge Profunctor into Base so that those libraries could begin offering prisms?
We had not previously planned on that, but if you wanted to try and talk to me about joining the Core Libraries Committee and maybe making a case for it. I personally do not have a plan for it at this point, just for various reasons. And we can talk more about that one offline. Text taggy lens gives a lens example. Lens ESON. This was actually written in response. There was a ESON lens package that was shipped out. Hideyuki Tanaka did one. And it unfortunately violated the laws, so we just sat down and wrote, what are the laws? If we just need cases to match on, is it a number? Is it a string, a Boolean, a null, what are the value or an object or an array? Just let us match on the things that happen in JSON. And then we can go through and just go look at key B as an object, convert it back into a hash map. And we can go back and forth between all of the different representations that we have available to us. And if you have an ESON instance for deserializing or serializing, you can read it out as a strongly typed thing in Haskell and try to match on it. And if it parses correctly as that, then that prism will match. And there's analogs to this in other languages. There's a monocle JSON library, as I recall, and PureScript has a similar component. Brian O'Sullivan has a library called Rec. I think it's Web Request. But it provides a lens-based API for all of its bits and pieces. So you can work with the response headers as an object that has a traversal that lets you walk each individual header or manipulate them or play with your cookies, build things up, tear them down, and then form requests or send a request, get it back the request, look at the response body, treat it as JSON, go in, walk the keys, all of the values, get the owner key, the login string out of it. And then this horrible thing that was going to be 20 lines worth of Haskell to go munge out one field out of a JSON document that came from some web service is a one-liner, or two-liners here. These are the things that make me happy about Lens, because this is all emergent phenomena. We've done a lot to try and support it, to try and make it so that anytime someone can make a reasonable case that something should work for a deep fundamental reason but doesn't currently, we find a way to use some kind of type magic to make it all go without trying to be Perl and make it up for some ad hoc reason. It should always be something I can tie back to some sort of category theoretic mumbo jumbo that most of the audience won't care about. But it makes me feel a lot better that I can actually understand what's going on or have a chance of solving it. And so we can look at these on types. We can look at, here's another ESON example. What else do we have here? Traversals, prisms. The monocle version of the JSON example. This is unfortunately way too washed out. But we can build prisms in Monocle just as well. You can build some JSON object and then match and do all the things. Now, the composition, this is a little bit more verbose than Dot, but it's the best they can do inside of Scala. And they have to deal with the separate cases. In PureScript, there are similar constructions for working with JSON. Taggy lens, we can work with XML with lenses like 3 or 4 different ways. Almost all of them need some form of access to prisms, or they can only parse. Diagrams, I was mentioning before, uses lenses, and they can use them in a lot of interesting ways. Like if you have a path in diagrams, how it was constructed is fairly open. But if you want to, you can look at a path that was made out of a bunch of points before, and you can try to match it to see if it's a Bezier curve. Right? And it'll try to decode the path into one. And if it is a Bezier curve, it'll give it back. It'll give you back the control points.
Yeah, we should get rid of that.
Perhaps. I was just trying to look for other interesting examples. Another one that comes up is this plated construction, which we stole from Uniplate. Uniplate has it's a generic programming library in Haskell by Neil Mitchell. It's used heavily internally inside of like HLint to go through and walk Haskell's ADT or GHC's ADT and try and, or the Haskell source extensions ADT, and figure out where you're doing things wrong. And it basically, once you've converted it into the lens vocabulary, it's a traversal that knows how to get, say you have an expression type, sub-expressions out of your expression type, immediate sub-expressions. So if you're looking at an addition, it's looking at the 2 additions directly below you, but not all the things, or the 2 expressions directly below that, but not all the ones below them. And then using those things as a building block, we can go through and give you the ability to apply rewrite rules and a whole bunch of other things, or go walk and find every occurrence of this in an entire subtree. So the combinators of lens can walk recursively. One of the rather amusing combinators in here is called ... which will take your lens, and if you're working in anything plated, it will just keep walking until the next lens or prism or the next fold thing that you're doing matches. Okay? And so if you're looking at XPath or something like that, and you have to encode it, and it has one of those kind of / or whatever I can't remember the XPath is for jumping, skip all this intermediate stuff and then start matching again. We could just directly encode that. There's evil magic, thanks to Gershom, which he will be mad at me for showing, which should be able to do things like, oh, I don't know, what do we have?
Just use first and second.
Hello world, and upon second, set it to, oh, come on. Oh, it's in data lens. That gives away how it works. There. So second is a function. We ran a field accessor backwards. What's a good one here? Upon second tail. No, what did I do wrong? Oh, tail that second.
Can you put the lambda?
Yes, what do you want to do?
Just write second as a lambda. You just do like try to point home.
Oh, why?
Yes.
That? There you go. Now this is evil, and it winds up building objects by injecting exceptions and doing horrible, horrible, horrible things it should never do. And there are cases you can use to screw this thing up, but it was written entirely to terrify people. And so that's why it's buried in data lens, with other lovely things like iPlate. Go find all the occurrences of strings in that thing on the side and go swap them out. So if you want to do generic programming and you just want to use your lens combinators, you can already do so. So you can scrap your boilerplate with lens. I suppose I should have done paper title. And I realize I am now over time by about a minute or so. So I will try to wrap up relatively quickly just by closing these windows out one at a time and saying something as I go past. So with linear, we can talk about, I have a vector space and I can go get the x coordinate out of it or modify it. Or if I have a matrix, I can go read the column for underscore x. There's literally column is a combinator that will take a lens and give you a lens that gets a column out of a matrix. That was actually the original motivation. We can play with things like my tables package, which was actually written as a spike solution to try and see what the world would be like if you just assumed lens. What if we didn't care about the lens laws? Because actually, if you use the lens package, the lens laws are there for you. You don't actually have to follow them. The lens package will still do the right thing. The only thing that happens is that the combinators are no longer the only possible thing that could work. They're not canonical necessarily. You could distinguish between a fused version of things or an unfused version of things. But everything still operationally behaves. So with the tables package, we went through and made it so like I might build nodes or here I can build tables that have multiple keys. So here I'm like looking at something like, here's a table. I can go through with any arcs that point to 3, fold and give me back all the names, or with all the arcs, or all the nodes that have a pointer to both 1 and 2, go fold and get me all the names of the nodes. Those kind of bits of terse code become very readily expressible. Now we had to give up the lens laws in order to make that sort of API usable, which was somewhat telling, and we wound up using this to feed a number of results back into lens as a sort of spike solution. Vinyl uses lenses internally for a bunch of things. Inside of like the last little talk that I gave, the little lightning talk where I showed my game engine that I was playing with, all of the options here are then just captured and made into lenses by this little bit of template Haskell. And then we can go through and take command line options and mix them together with however my input is going to work for my key codes and scan codes. And all of these things can be built into a larger and larger internal system. And then because of the way these things are all built up as classes, I can directly use any of the lenses that are designed for one of the parts on the larger construct. So I don't have to remember the entire path down, because there's only one in the way things are constructed. So the classy lens construction has been a big help for a lot of people. And it's kind of reduced a lot of pressure on the overloaded record fields kind of front. In Ermine, our little compiler at S&P Capital IQ, we have a number of syntax tree types with different notions of application. Let's go find the application node. Or let's go find the variables. Try to case match whether or not this thing is the var constructor or whatever in my syntax tree. Our core here, let's see if I got a good, where's core? I realize I'm flipping past random examples. Ignore hardcore. We have core and hardcore. Hardcore was really just chosen for the name. But it's the bits of core that you can unify just by comparing for equality. And then we have our actual notion of core here, which has whatever kind of annotations we're using, whatever our variables are. But then we can go through and match on the variable case. Our unifier for types and kinds, can be largely parametric over the choice of syntax tree that we're working with, et cetera. All of these things build on top of this foundation, even though they bear very little resemblance to one another. So my original goal with Lens was to build a vocabulary I'd still be using in 2 years. It's 3.5 years later, so I guess I've technically passed my original muster on my original goals. We have a Haskell Lens channel on Freenode. There's about 160 people in there at almost all times. Most of them are very happy to answer questions about Lens if you're trying to get started. It's incredibly difficult to get started with Lens just by reading the API. So come in, ask questions, and we're more than happy to help out. Okay, so that is everything that I have that I wanted to say today, and thank you very much for your time. I think we've run a little past, so if anybody wants to grab me with questions or whatever, feel free to just ambush me later. Well, before too long.